Hello, everybody. I'm Dr. Shafiq. I would like to welcome all of you in this video session. In this session, actually, we'll talk about eccentricity of foundation. Like if you apply a load which is not working at the center of the foundation, then basically you will see some effect of eccentricity. Okay. Now let me share my uh, screen with you. You can see here that this is our foundation here, and there is a load here, and there is also a moment here. Okay. The equivalent system, we can just draw that one that actually the load is working a little bit away from the center of that foundation. So this one is creating a moment. What is that moment? That Q multiplied by E. Okay. So from the mathematical calculation, you can see that when your E is actually equal to B by 6, then basically this one would be 0 at that corner and would be maximum in this side. Okay. It's just like a let's say you are sitting at the middle of a boat. Okay. So if you move yourself to the right a little bit, then you will see that the right side is going down and the left side is going up, right? So when you are moving in such a way that your E is just equal to B by 6, then basically you will see that the other side is actually having zero pressure. Okay. So in that situation, you can understand that when there is a eccentricity, basically the load distribution on the soil is not equal. So we usually try to make sure that the maximum, like pressure on the soil would be less than allowable bearing capacity of the soil, right? So how usually we do that one? There are several methods to do that one. I'll just try to show you one by one. And uh, let's see the first one here. First of all, you can see this is like the combined uh, stress. Like here, you can see because of the load Q, the stress coming in the foundation would be Q divided by the area of contact, right? And then you can see there is a moment here that will try to, like rotate that one this direction little down and this direction up. So the effect of moment will cause the bending stress, right? So here in this picture, you can see that your Q means like the pressure is equal to Q by A plus minus MC over I. Okay. So when we are talking about Q max, here is your Q max, then this one would be positive. When we are trying to see Q mean, then this one would be, the sign would be negative, right? So this is your axial load. M is the moment, total moment. C is basically half of B by 2 here. And A is the cross-sectional area of the member, and I is the moment of inertia. Okay. So first of all, we are here actually trying to see that one-way eccentricity. Okay. So you can see that this is your foundation plan, and the load here is the center of the foundation, but your load is working here. Okay. The column is actually, the center of the column is here. So you can see the distance from here to here is E, and this is your Q. So this one is causing a moment of Q into E. That's your moment Q into E. The area of the foundation is B into L. And C is basically B by 2. C is equal to B by 2. This is your maximum Q, and this one would be your minimum Q here. Okay, so this is the axis here. So this is B by 2, this is also B by 2. And what's the moment of inertia along this axis here? That would be actually LB cubed by 12, right? LB cubed by 12. This is kind of like very similar with your mechanics of solids class. Now you can see here that you know your moment equal to Q by E. So if you change your Q max that and change that value, then Q by A, which is BL, A is the BL, and then this one is basically your this part here, 6m by b squared L. So if you change your m is equal to QE, then basically you get this equation. Okay. Similarly, if you try to do that one with your Q minimum, then basically you get a negative sign here. So what you see from here, you can see again, like what I said earlier, that if you plug that one here is Q minimum is 0 and solve for your E, then basically you will get E equal to B by 6. Okay, so when your E is equal to B by 6, then this one will be 0 and this one will be Q max. Now if you increase your E more than B by 6, then basically you will see you are going like this. You are going like, here is a tension part here. But since soil doesn't take any tension, so we are showing from here to here all the way. This one is 0, and then this one is increasing from here. So in that situation, that if this is the width of the foundation, then you can see only a small part, not a small part, but a fraction of that part from here to here, like we call that one B prime, multiplied by the L. That's actually the effective area where the load is going to be distributed. Okay, so based on that, actually there are several methods proposed by several researchers. So first of all, we can see the effective area method by Meyerhof, okay, in 1953. So this is the step-by-step procedure. So first step, what you have to do, determine the effective dimension of the foundation. Means like which part of the footing is actually taking load. Is there anything, like they are not taking load there. So basically, you see the B effective is equal to B minus 2E. Since this is one-way eccentricity, and this is only in the B direction, not in the L direction here, for this particular problem. Many cases that could be in the L direction, not in the B direction, right? So one-way system, let's say the eccentricity is in the B direction, then basically your effective width is B minus 2E, and your effective length is L. So what would be your effective area? That would be L into B minus 2E, right? Similarly, if your eccentricity is in the L direction, then the effective length would be L minus 2E, and effective width would be just B. And in that situation, your effective area would be effective length L prime B, okay? And then the smaller of the two dimension is the effective width of the foundation. So once you change your effective width and effective length, then basically sometimes your B and L can be changed. As we said earlier, that your L is the bigger of the two. So if you subtract something from your L, then basically your L prime could be less than your B. If this is the case, then your B will be actually your L prime, and your L prime would be your B prime, okay? Now, step 2, that you have to use the same, ultimate bearing capacity formula here with all those factors here, okay? But you have to remember very carefully, this is one of the most important part of these problems, is that when you try to find out your shape factors here, like FCS, FQS, and F gamma S, then basically you have to use your effective width and length, okay? But when you are gonna find out your depth factors like FCD, FQD, and FQ gamma D, then basically you have to use the original or actual width and length of the foundation, okay? And definitely at the last term actually here, this one is always effective width, okay? Now you can see here that your total load carrying capacity, ultimate load carrying capacity would be bearing capacity multiplied by the effective area. This is basically your effective area, P prime, L prime. Okay, that's the effective area. And QUE is the average load per unit area of the foundation, which is here, if you see that here, okay? So let's say this one is working down there. Now, this is your, because of that thing, actually, this is your effective, like width is from here to here. This means like only this width is taking, if you see this figure here, that this is the only width that's taking, these are taking load, okay? The blue color here, that's actually taking the load. On the other hand, this one is not taking any load. Okay, so your area is decreasing. So if you want to find out the equivalent load that's working only this part here, then basically you can use this equation that Q U prime into B minus 2E divided by B. That's your equivalent area, okay? Your actual area is B into L, but your effective area that's taking the load, that would be B prime into L, okay? So this area here, the blue area here. So if you distribute the same load here, this area, so you can see that's actually the difference between this and this, okay? So a small fraction of that is actually working when you have eccentricity. Now, again, your factor of safety, you have to use that one. That's actually QU divided by factor of safety. That would be your Q allowable. Okay, so Q allowable is equal to QU divided by factor of safety. Now, this is a problem that I'm going to show that one in the board in your companion video. Okay. So this one is saying that eccentrically loaded foundation is shown below. Use a factor of safety 4 and determine the maximum allowable load that the foundation can carry. Use Meyerhof's effective area method. Okay. Now there is another method here. It's called the Prakash and Saran methods. Actually, there are many other methods there, but our author just let's summarize some of the best like are widely used equation in the actual field. Okay, so this is Prakash and Saran's method. This is only applicable for continuous foundation. Okay, continuous footing foundation. So what he is saying the ultimate load per unit length of a continuous foundation is determined by the equation QU is equal to CNCE QNQE and half gamma BN YE. Actually, that would be gamma E. So these are basically the bearing capacity factors under eccentric loading, okay? Bearing capacity factors, but you can see here that there is no shape, depth, or inclination factor here, okay? If you want to use the shape factor, they provided also that information to you. But first of all, we need to know how we can find out the bearing capacity factors like NCE, NQE, and N gamma E, right? So these are the charts to find out this information. This is your friction angle, and this is your NCE. This is your friction angle. This is your NQE. Similarly, this is your friction angle, and this is your N gamma E. You can also see that this is your E by B, okay? That starts from 0, means like no eccentricity. This is 0.1, 0.2, 0.3, 0.4. Okay, if you know this one, and if you know the friction angle there, you can just find out what would be your NCE, NQE, and N gamma E. Then you plug that one in that equation, and you can get it much easier way, okay? Now, if it is like a rectangular footing, then basically you have to use the FCSE, FQSE, and F gamma SE. This is not the same shape factor that we use the general bearing capacity equation. There is a E here, means like that for eccentricity, okay? So, and they gave you that formula here, that if there is eccentricity and this is a rectangular foundation, then basically you have to use rectangle or square foundation, then basically you have to use these terms there, okay? So here is one of the example, that the same example what I was showing you for example 4, this is the same example, but the other one was to do that one using Meyerhof's method. Here they wanted you to do the problem with following the Prakash and Saran method, like what we learned right now, okay? So here you can see this is your foundation, 1.5 meter and 1.5 meter size, and you can see there is actually the force Q is working down there, and the eccentricity in one direction, which is 0.1, and gamma equal to 17 kilonewton per meter cube. Cohesion is 0, so this is basically granular soil, and phi equal to 32. Okay, and you can see this is basically not a continuous foundation, this is a square foundation. So we have to use the shape factors here, right? And your DF is 0.8 meter here. Now, let's try to see that how we can do that one. So basically, our Q allowable is equal to Q ultimate divided by 4. And then we can just say this is your actually BL by 4 is equal to, this one is basically equal to Q NQE FQSE plus half gamma B N gamma E and F gamma SE. Now from the value of Q prime is 32 and EB by B equal to 0.1 by 0.5, which is 0.067, okay? We have to find out the value of NQE and N gamma E. Since it doesn't have any cohesion, so cohesion part is 0 here, okay? Now, if you go to the next picture here, then I tried to show that one, like for 32 degree, if you just go here, I don't have any curve for 0.067, 0.067. So I just assume this one is just like, hey, 1/3 from here and 2/3 from here, another line here, okay? So if you try to find that out, actually you get your NQE is 23.6. Similarly, if you do the same thing here, this is 0.1 and this is 0. So I'm just assuming that 0.076 is along this line here. Okay, so if you get that one, then basically you get the value of N gamma E is 19. Okay, so what we are gonna do, we are just gonna plug these values in this equation, but before that, we can also find out your FQSE and F gamma SE. So your F gamma S, FQS by default 1 and F gamma S is equal to this one. So once you get this value, then basically you just plug that value here and try to find out your QL out. Okay, this is the area actually. This is the area, total area multiplied by the ultimate bearing capacity. So if you just QU multiplied by the area divided by your factor of safety, that's basically your overall loading capacity. Okay. Now let's move forward. There is another method, but this one is only applicable for granular soil. Okay. And you can see this is Prakash and Saran. They propose that method. They are saying that QUE, E means eccentric, is actually 1 minus RK into QU centric. Centric means like the load is working at the center of the foundation. No eccentricity there, right? So you find out the QU centric the usual way using the general bearing capacity formula, and then you multiply that one with a reduction factor, okay, 1 minus reduction factor, then you get your QU for eccentricity, okay? But to find out your, like RK reduction factor, that's actually RK is equal to A E by B. Okay, E by B, E is the eccentricity, B is the width, A and K are the factors, okay? The two factors, A and K are the two factors. And QUE is the average ultimate bearing capacity of eccentrically loaded continuous foundation. And QU centric is the ultimate bearing capacity of centrally loaded continuous foundation, okay? So we have to find out the Q-centric as usual method, and then we have to find out your RK. But RK, to find out your RK, you also need to know your A and K, which is given in this table, and actually follow the equation here, this equation here. So this one depends on your DF by B. If your DF by B is equal to 0, then basically your A would be 1.162 and K would be 0.73. Similarly, if your D by B is 0.25, 0.50, 0.1, then basically 1, then basically you can find out this value of A and K. Once you get that value, you just find out your RK. And if you know your RK, you just plug that in your equation and you can find out the ultimate bearing capacity for eccentrically loaded foundation. So here is your example, the same example actually. Is it the same? No, it's not the same example, but a little bit different here. So you can see here that for an eccentrically loaded continuous foundation on sand, given B equal to 1.8, DF equal to 0.9, EB by B equal to 0.12, one-way eccentricity, gamma equal to 16 kilonewton per meter cube, and phi prime is equal to 35 degree. Using the reduction factor method, estimate the ultimate load per unit length of the foundation. Okay, so that's basically a continuous footing. Okay, and since this is only applicable for granular soil, so cohesion is 0. So you can see for your centric, QU centric, there is no cohesion term here because of C equal to 0. So you have these two terms here, okay? So once your phi prime is equal to 35, your NQ is 33.3 and N gamma equal to 48.03. That's you are getting from the table 6.2, okay? That's for the factor, bearing capacity factor for general bearing, like a capacity equation. Now you can see, since this is like a continuous foundation, so you can see this is QS and gamma S equal to 1, gamma D equal to 1. You just find out your QD from there, and this is basically your centric value, okay? Now you have to find out the reduction factor. To find out the reduction factor, you need to know your D by B, which is 0.9 by 1/8 is 0.5. So if you go to the table for dA by B 0.5, you get your A and K from there. Okay, let me go back there and show you. So dA by B is equal to 0.5. So this is your A 1.754 and your K is 0.8. Okay, so that's what they are using here, 1.754 and 0.8. So once you plug that value here, you already know E by B, which is given here, which is 0.12 to the power 0.8. So if you calculate that one, then basically you will get a QUE, okay? And then you multiply that one with the area. And they are saying the area is like one unit in this direction, okay? That's actually L or B is 1, and this one is here, B is 1.8. So the total area would be 1.8 into 1, that's actually 1.8, okay? Now we are going to talk about the eccentricity, like in both ways, okay? So here is the picture of that thing, okay? You have eccentricity not only here, this is your EB in the B direction, and this is your EL in the X direction. So the force is actually working here, okay? The other way I can say that this is the footing, but the center of the column is here, and the load is coming QU, okay? So this one is not only creating, like a compressive force, but also creating a moment. Now you just think about like, hey, this is a boat, okay? If you sit here at the center, then basically your boat is just, like staying stable. Now, if you move this direction, you can understand that this corner will go down, this corner will go up, and these two corners will also go a little bit down or up based on like, hey, what is my EB and EL here, okay? So let's see how we can solve this type of problems, okay? So here you can see your EB is your moment divided by your Q. Sometimes this one will be given, sometimes your moment and Q will be given. You have to find out your EB. Similarly, your EL means like their eccentricity in the L direction, eccentricity in the B direction here. And your QU is equal to your QU ultimate bearing capacity multiplied by the area of the foundation, okay? So area of the foundation, A prime, is actually the effective area, B prime, L prime, because the whole area of the foundation will not take the load, right? So a part of the foundation will take the load because of the eccentricity. Now, we usually use the same equation, general bearing equation, to find out our QU, okay? But again, you have to remember that one, as I said earlier, that when you are trying to find out the shape factors, then basically you have to use your effective width and length, okay? When you are trying to find out your shape factors, effective width and effective length, that's what you have to use. When you are trying to find your depth factors, then basically you have to use your actual B and L. Okay, is that clear? This is very, very important. Okay, you have to remember that one. So when you are trying to find your shape factors, only then you have to use the effective width and effective length. When you are trying to find your depth factor, then basically you have to use your actual L and B rather than instead of like your effective width and length. Now, and remember that the last part here, that should be always effective width here. Okay. Now, to find out the A prime, B prime, and L prime, okay, there are 5 possibilities or 5 different cases we usually consider. Okay. Now we'll just see each of the cases separately. And when we do the problem, basically we have to first see that which case actually our design is, our problem is. So based on that, we have to solve the problems, okay? Now see here, this is our case number 1. So you can see your EL by L is greater than 1/6 and EB by B is greater than 1/6. Both are greater than 1/6. If both are equal to 1/6, then basically you will see something like this from this corner to this corner, okay? But since they are bigger than that, so some part here has tension, some part here has tension, but since soil doesn't take any tension, so we are showing that one as 0, okay? So they are not taking any load here. So who is taking the load? That's actually our effective area here, okay? Now, if you see what is that effective area here, you can see this is now B1, this is L1. Okay, so what's the area of that? Half into B1 into L1, right? That's what is showing here. Half into B1 and L1. Where B1 is, you can just calculate the value of V1 and L1 from here. Okay, if you can calculate that value here, and then effective length would be larger of the two, of L prime and B prime. Okay, and if you get the larger one as your L prime, then your B prime would be the area, effective area divided by L prime. So you'll get your effective width. Okay, so this is, both of them are greater than 1/6. Okay, this is case number 1. How about case number 2? EL by L is greater than 1/6, but EB by B is less than 1/6. So you can see EL by L is greater than 6. That's why you see some 0 here. Okay. But EB by B is not greater than 6. That's why you see a little bit here. What happens if your EB by B equal to 1/6? Just 1/6. Then this one should be here. The line should be something like this. Okay. So your L2 would be 0 at that time. Anyway, so you can see this is basically a trapezoidal section. So what's the effective area of that? That's this plus this divided by 2 multiplied by B, right? So L1 plus L2 divided by 2 multiplied by B. That's your effective area. Now, once you find out your, try to see that which one would be your bigger, like L prime, or the larger of the L1 and L2. Okay, the effective length would be larger of L1 and L2. And then you just try to find out your B prime using this equation, like your effective area divided by your effective length. Okay. Now, the important thing is for case 1, you can see, you can find out your B1 and L1 from the formula. But here, actually, we use this chart here to determine our L1 and L2. Okay. So you can see here, this is your L1 by L and L2 by L. This is EL by L. And these are the lines here, which is EB by B. So to find out the L2 by L, you have to use the chart in this direction. Okay, so your EB by B would be either this one, this one, this one, this one, this one, this one, or this one. Okay. If you want to find out your L1 by L, then basically you have to use this EB by B. Okay. So I'll show you, like the example that how to use this chart to find out your L1 and L2. So if you find out your L1 and L2, then you try to see which one is bigger. Okay, that would be actually your effective length. Then you find out your effective width. Just divide your effective area divided by the effective length. That's your effective width. Okay. Now, here is your case 3. This one is saying that EL by L is less than 1/6, but EB by B is greater than 1/6. So you can see there is some. In the B direction, you see 0 here. Okay. In L direction, you don't see anything because this is less than 1/6. This one is very similar. You have to find out the area. What is that area? This multiplied plus this divided by 2 and then multiplied by L. So B1 plus B2 divided by 2, then multiplied by L. Okay, that's your effective area. Now, actually, you have to find out the same way what would be your B1 and B2. Okay, so you can see your L is not changing, but your B is getting smaller. So your L remains as L. Okay, the effective length remained as L. And you try to find out your B1 and B2 from this chart here. Okay, so here, this way to obtaining B1 by B. So B1, if you get any value, so your B1 would be that value multiplied by B. Okay, similarly, you can go this way to find out your B2 by B. In that situation, like you use this EL by L from this direction. From that direction, that's actually EL by L, that's for B1 by B, and that direction for B2 by B. Okay. Now, case 4. Case 4 is both of them EL by L. L is less than or equal to 1/6, or EB by B is less than or equal to 1/6. As I said earlier, if they are equal, then basically the line would look like this. Okay, so B2 and L2 both would be 0 if they are equal to 1/6. If they are less than 1/6, then basically in B direction or L direction, you don't see any 0 here. Okay, so this is your total area. So what's the total area, effective area now? That you can just draw a line here. Okay, so for that part, that would be L2 into B, right? That's a rectangle here. L2 into B. So L2 into B. And then for this part here, you can just get this plus this divided by 2 multiplied by the length from here to here. Okay, so length of this trapezoid would be L minus L2, right? L minus L2. From here to here is B. This is B2. So B plus B2 divided by 2 multiplied by the distance from here to here, which is L minus L2. Okay, so you can find out your effective area here. Now you can see your L remains your L. So you just try to find out your B prime from A prime by L. But anytime if you see your L prime and B prime, L prime is smaller than B prime, as soon as you see that one, you have to, uh, you have to just rotate that one. Means like you have to change your L prime as B prime and B prime as L prime. Always try to remember this one, that your L or length is always bigger than the width, okay? Now see the case number 5 here. Oh, this is also for like how to find out your actually B2 and L2 in this equation. How to find out your B2 and L2 here, okay? So this is the chart here. And again, you can see for obtaining B2 by B, these are the lines, okay? These lines here. When you're trying to find L2 by L, these are the lines, okay, for different EL by L. Now, case number 5. This one is for circular foundation, okay? So for circular foundation, wherever you put your load on the circular foundation, this is always like one way, right? So because you can draw a line, like from the center to your periphery through that line, and you can say, hey, this is just one way eccentricity. But you can see if you know your ER by R, then basically you can find out your A prime by R squared and B prime by R squared. From A prime by R squared, you can find out your A prime, which is effective area. And this one is from here, you can find out your effective width. Once you get your effective area and effective width, you can find out your L from there, which is effective area divided by effective width. Okay, that's the way you usually do this problem. And again, remember that one. Once you get that one, then to determine the shape factors, you have to use the effective B and effective L, right? And to find out the depth factor, you have to use the actual L and actual B, okay? Then you just plug that one into the general bearing equation, in which the third term, the B should be replaced with B prime all the time, okay? That's the understanding for this like two-way eccentricity. Now, there is a problem here. Actually, I'm going to do that one in your the other companion video, okay, in the Blackboard. So you can see this is actually a easier way to do that one, okay? So which is a simple approach, actually. You can see here that if you take like 2E out from here and 2L out from here, so this blue area is the effective area that's going to take the load here, okay? So you can use that way to find out the effective area, and then you can just multiply that area with your, this is your effective B, which is B minus 2E, and your effective L is L minus 2EL. Once you get that one, then basically you use this one as a rectangle. Okay, so the effective area would be B prime into L prime, and then use the same thing in your bearing equation, ultimate general bearing equation, and find out the overall capacity of the foundation. Okay, so that's all for today, and I'd like to see that if you have any question or not, you are always welcome to Skype or FaceTime me during the office hours. Okay, thank you so much.